Students, welcome to the fifth session of our third module in compressible fluid flow. So, we have been discussing about normal shock waves. So, we have derived various relationships called Prandtl-Meyer relationship, Rankine-Hugoniot relationship, etc. And now we will do some numerical problems based on normal shock waves. Okay, before that, I just forgot to tell you about the depiction of a normal shock in our HS diagram or Mollier diagram. So students, it is very important that you should know how to depict a normal shock in HS diagram, right? So actually, before depicting normal shock on HS diagram, you should know about two different type of flows. You have already studied a type of flow called isentropic flow, but there are different other flows like Rayleigh flow and Fano flow. The Fano flow is a flow which is purely driven based on friction, and Rayleigh flow is a flow which is purely driven based on heat transfer, and isentropic flow is just as a flow based on a flow driven based on variation of area change is required in isentropic flow. Fano friction is required in Rayleigh flow. Heat transfer is required. So you will be learning about Fano flow and Rayleigh flow in the subsequent modules, but I'm just giving an overview because you need to know about Fano flow and Rayleigh flow before drawing shock wave. Okay, suppose this is a Fano flow will be like this. Okay, somewhat like this, and Rayleigh flow will be like this. So the point of intersection of Rayleigh and wait. The point of intersection of Rayleigh and Fano flow. If this is Fano flow, Fano, this is a Rayleigh. The point of intersection of Fano and Rayleigh will be normal shock. The line joining the point of intersection of Fano and Rayleigh will give you a normal shock line. So students, it is very important to note that this is a normal shock is not an isentropic process, so there will be an entropy change. We have derived the equation for entropy change and all. So this will be S1, this will be S2, okay, and S1 will be equal to S01 itself, S2 will be equal to S02 itself, right? So but we know that if this is 1, if this is 2, we know that the the stagnation enthalpy for both the states, stagnation enthalpy will be same for both 1 and 2. So H01 will be equal to H02, it will be equal to H0, right? So both will have same value of stagnation enthalpy, and if stagnation enthalpy same means stagnation temperature will also be same. Okay, but stagnation pressure will be different because they are at a different position, right? So this will be P01 and this will be P02. So stagnation pressure will be different, stagnation temperature and stagnation enthalpy will be same. So that is why we have derived equation for P02 by P01 and all. So we have derived an equation for stagnation pressure ratio, right? Stagnation pressure ratio equation was derived because P021 and P02 and P01 are different. They are different from each other. But H01 is equal to H02 and T01 will also be equal to T02. So most of the equations were derived based on this particular aspect of normal shock. Okay. So this much you should be learning. You should understand these concepts, then only we can do problems, right? So now we will move to we will do some 2-3 problems based on this normal shock, and I will give you some assignments, and beyond those assignments You should do some problems on your own from referring to some good textbooks. Okay. So students, this is a problem based on normal shock. So air with a pressure and temperature of 100 kilopascal and 10 degrees Celsius passes through a standing normal shock wave where flow Mach number is 1.6, right? The density and temperature of the air after it has crossed the shock. Okay. So in this problem, a Mach number and flow properties upstream of the normal shock. Suppose this is a normal shock. Okay, this is the normal shock. This is the upstream section 1. Upstream section. This is the downstream section 2. So in this problem, Mach number M1 is given. M1 is equal to 1.6. And what all things? Pressure P1, upstream pressure P1 is 100 kilopascal, right? And temperature T1 equal to 283 Kelvin given, right? So we are asked to find downstream properties, right? Determine the density and temperature of the air after it has crossed. So actually ρ2 and T2 should be found. ρ2 and T2 should be found. P2 is not given, but P1 is there, M1 is there, T1 is there, ρ1 is not given. Okay. So how to find these ρ2 and T2 downstream the normal shock? This problem can be solved using the relationship. So if you know the value for P2 by P1 across the normal shock, you can get P2. If you know that temperature ratio T2 by T1 across the normal shock, you can find T2 if T1 is not. T1 is not, and ρ2 can be found using P2 by RT2. For perfect gas, ρ2 equal to P2 by RT2. So if P2 and T2 are known, then you can find ρ2 easily. So how to solve this? So you may have the equations for P2 by P1, T2 by T1. All those equations are derived in our previous sessions. But what is the peculiarity of our compressible fluid flow? So all these ratios we are deriving in each sections, like even if the case is with isentropic flow or normal shock wave, all these relations can be formulated as a function of Mach number or gamma. So they can be tabulated. If Mach number is known, they can be tabulated. So normal shock wave tables are available. So let us have a look at a normal shock wave table where you may have the value for P2 by P1 for a particular Mach number, right? So we know that P2 by P1, we derived an equation for P2 by P1 as a function of Mach number 1 and gamma. Upstream Mach number. All ratios are based on upstream Mach number, right? Do you remember the equation? Do you remember the equation for P2 by P1? Okay. So I will tell you the equation for P2 by P1 is like gamma plus 1 by gamma minus 1 into 1 plus gamma m1 square by 2 gamma by gamma minus 1 m1 square minus 1. So this is a very large equation where you have to substitute m1 and gamma. But instead of substituting this equation, you can directly approach the gas tables. So let us have a look at gas table. Students, here you can see the gas table for we require gas table for normal shocks, right? Normal shocks. So here you can see at fourth section is normal shock. We should take gamma equal to 1.4 because this is for air, right? For air, gamma is 1.4. Page number 81. 81. Sorry, not page number 81, it is page number 52, right? 52. Okay, this is 52. So students, you can see that normal shocks in perfect gas, gamma equal to 1.4. For corresponding, mx means upstream Mach number, my means downstream Mach number. So our upstream Mach number is 1.6. So students, you note that here, okay, 1.6, the last one. So for 1.6, corresponding m2 is 0.668, right? And what all things we require? Okay, P2 by P1, that is Py by Px, and Ty by Tx is in the third and fourth column. So note those values for corresponding to 1.6, 2.82 and 1.388. Okay, note that value. So P2 by P1 for Mach number 1 equal to 1.6 is 2.82, and similarly T2 by T1 corresponding to M1 equal to 1.6 is how much? 1.38. So we have got the value for these ratios directly from the table instead of applying the equations. So applying equations is tiresome or cumbersome. So it requires a lot of time. So the procedure is simplified if we use uh, gas table. So P2 by P1 at a Mach number equal to 1.6 is 2.82, but P1 is equal to how much? P1 is equal to 100 kilopascal. It's given in the question. So P2 can be written as P1 into 2.82. It means 100 into 2.82 means 282 kilopascal. So that is the downstream static pressure. But pressure is not asked, density is asked. So in order to find density, we need to find T2 also. So T2 by T1 corresponding to M1 equal to 1.6 is 1.388, and T2 can be written as 1.388 into T1 means 1.388 into T1 is 2, how much? 283 Kelvin, means you will get a value of 392.8 Kelvin. Okay, so T2 was asked, so T2 is found. Rho 2 was asked, rho 2 is P2 by RT2, and P2 obtained will be 282 kilopascal, right? So you have to change into SI, Pascal, then only you can divide with another SI unit. And R is 287. You know the value of R for air, and temperature is 392.8, and you will get a value around 2.5 kilogram per meter cube. So density is option. So this is the procedure for finding the answer for this particular equation, this particular problem. Okay, problem across a normal shock. So students, this is another problem. A compression shock occurs in a divergent airflow passage. Okay, so we have a divergent airflow passage, and on the upstream side of the shock, velocity of air is 400 meter per second, and the pressure and temperature are 0.2 megapascal and 35 degrees Celsius. So there is a shock upstream and downstream is taken as section 1 and 2. So the velocity of air upstream is V1 equal to 400 meter per second, and pressure and temperature are P1 equal to 0.2 megapascal, T1 equal to 35 degrees Celsius means 308 Kelvin. Okay, 308 Kelvin. You should convert it into SI unit. Okay, this much data are given. Now we are asked to determine the Mach number and air velocity on the downstream. So M2 should be found. V2 air velocity at downstream should be found, and change in entropy S2 minus S1 should be found per unit mass of air. Okay, per unit mass of air means small s2 minus small s1, specific entropy. Okay, so that is specific entropy. Now this much parameters should be found. Only these three parameters are given. So students, in order to find M2, if M1 is known, we can directly find M2. How? Because in our table, M2 downstream Mach number for corresponding upstream Mach number is directly given. Okay. So if M1 is known, M2 can be found. So how to find M1? M1 is nothing but V1 by A1. Actually V1 is given, A1 is root gamma R T1. Right. So T1 is known, V1 is known. V1 is how much? 400 by root 1.4 into 287 into 308, and the value is found as 1.14. So students, Mach number in the upstream is found. So corresponding to 1.14, you can find M2 as a function of M1 is given in M1, and gamma is given in the table, right? So we can check the table now. The students, in this table you can see that normal shock for perfect gas gamma 1.4. Upstream Mach number is around 1.14. So this is 1.14. So corresponding to 1.14 downstream Mach number, yes, it is already available in the table 0.882. So M2 is 0.882, that is obtained. So M2 is obtained as 0.882. Now we are asked to find V2. So V2 is nothing but M2 into A2, and M2 into A2 means M2 into gamma R T2. So if T2 is known, we can find V2. So how to find T2? So T2 by T1 is corresponding to Mach number upstream. Mach number upstream is M1 equal to 1.14 is obtained as from the table T2 by, okay, you can, it will be 1.090. So you will get T2 as T1 into 1.090, and T1 is 308 into 1.090. So you will obtain T2 as how much? 308 into, it will be around 335 Kelvin. So 335 Kelvin means M2 will be, sorry, the velocity at downstream will be M2 into gamma R T2, right? So M2 is how much? M2 is 0.882, right? 0.882 into root gamma is 1.4 into 287 into 335, 335, and the value will be around 323 meter per second. So the value may not be exact value, actually it is around 324. Okay, 324. Now velocity and Mach number downstream is obtained. Now we are asked to find S2 minus S1. So students, you know the equation for S2 minus S1 as R log P01 by P02. You have learned. So you should know the equation for change in entropy. This may not be given in your data book, but this ratio P01 by P02 is given in the data book. So you can see here. Okay, here P02 by P01 is given. P02 by P01 is given. It is 0.997. So P02 by P01 is R log inverse, right? Inverse of 0.997, and R is 287, right? 287 log natural log 0.997, and the value will be 0.862 joule per kilogram Kelvin. 0.862. So this is how you find change in entropy. Students, have a look at this particular problem. The exit to entry area of a divergent duct is 1.4:1. So students, we have a divergent duct. Okay, divergent duct. So here you can draw a divergent duct here. Okay, so the exit area, let this section be, let this section be exit, and this area be A. Okay, exit area to entry area. So this be entry, inlet area be AI. This section be I. The Mach number actually it is at the inlet and exit are, this is inlet. Inlet Mi equal to 1.7, okay, and Me equal to 0.5. It's actually Mach number at the inlet and exit, okay. Now a normal shock occurs at the duct, occurs in the duct. So a normal shock occurs somewhere in the duct. Let there be a normal shock, and section upstream the normal shock be 1, section downstream the normal shock be 2. Assuming isentropic flow of air before and after the shock. So here isentropic flow, here isentropic flow. Determine a location of the normal shock. So we have to find the location of the normal shock, percentage loss in stagnation pressure, and change in entropy across the normal shock. So these are the things to be found out. So only data given is Mi equal to 1.7, Me equal to 0.5, and ratio AE by AI. Exit area to inlet area is 1.4. These are the only data given. So students, if area ratio is given, you could do one thing. AE by AI can be written as AE by A1 into A2 by A1. Sorry, A2 by AI. So students, what is A1? A1 is the area at this section, and A2 is the area at second section. So students, we have studied some assumptions while we were deriving an equation, governing equation, or the Prandtl equation for normal shock, that it occurs at constant area. It occurs at constant area means 1 and 2 should be equal. That is why I have written AE by AI as AE by A1 into A2 by AI, because A1 and A2 will be, A1 is equal to A2, so you can write AE by AI as AE by A1 into A2 by AI, A2 by AI. Okay. So suppose if this section is taken as 1 and this section is taken as 3, and in between the normal shock section is 2, AE by AI can be written as AE by A2 into A1 by AI, right? So since the process of flow between the section 1 and AI is isentropic, and between E and 2 is isentropic, there will be a critical section in between. There will be a critical section in 1 and 3. Critical section means A star section. Some A star sections will be there because they both are isentropic flow. So AE by A2 can be written as AE by that critical section A star in the third region into A star third by A2. So this is written like this, into A1 by AAS, A1 by A1 star into A1 star by AI, right? So this is written like this. So this is very important. You should arrange like this, then only you can solve these kind of problem. So the same method applies in any type of problem you encounter, which is similar to this one. So have a look at this equation. So here A2 and A1 is same, so you can cancel this. So this equation get reduced to A by A third star into a third star by a2 into a1 star by ai, right? So this much it get reduced to three different terms. So I will write it once more. A by ai can be written as a by a third star, ae by a third star into a third star divided by a1 star. So actually a2 is gone. This is wrong, right? Okay, you cancel that. So what remains is a1 star remains, a remains, a third star remains. So a star, a1 star into a1 star by a. This is what remains after cancelling a1 and a2. a1 and a2 is cancelled now because a1 and a1 is equal to a2. Now students, have a look at this equation. A by a third star means, you can see here, ae by a third star means, so the area here and the area in the A star critical section in the third region. So since this flow is isentropic, you can get the value of this based on ME, Mach number E, from the table of isentropic table. And this is also isentropic flow. So I star by ai can be obtained based on mi from same isentropic table, and this is unknown, but this is known, this value is 1.4. So students, from the isentropic table you can get the value of a by a star values for different Mach number. So Mach number 1. Actually ME is 1.7, right? Sorry, ME is 0.5, and this value is from isentropic table. You will obtain this value as, wait. So students, this is isentropic table, isentropic flow. So corresponding to 0.5 and 1.7, two Mach numbers are there, 0.5 and 1.7. So you can note that. So you will obtain the first, second, third, fourth, fifth. Okay, fifth table is a by a star. So a by a star value for m corresponding to 1.7 and 0.5. So you obtain that value, that particular value. Okay, 0.5 is somewhere, okay, the 0.5 is there, 0.5 value is 1.337, right? 1.34, and corresponding to 1.7, you will obtain the value as 1.337. Okay, so this value is corresponding to 0.5 is 1.34, and a by a star corresponding to Mach equal to 1.7 is 1.337. And now you should understand that this particular value is a star by a. So it should be the reciprocal of 1.337, right? So this is actually mi is 1.7, this is 0.5. Actually this is a star by a star by a is reciprocal of a by a star. So this is not one, and this is also not. So this unknown can be 4. Actually 1.4 is equal to 1.34 into a3 star by a1 star into 1 by 1.337, and a3 star by a1 star is obtained as 1.4 into 1.337 by 1.34. This value will be 1.397. So A3 star by A1 star is obtained. So students, why are we trying to find this particular ratio? What is the use of this ratio? So if you want to understand the use of this ratio, you should know that for an isentropic flow, you have learned that m dot into T0 by A star P0 equal to a constant. So this equation you have learned while you are studying isentropic flow. So you just rewind or turn back your pages, or rewind your video or try to obtain that section from your Moodles, that mass flow rate is a constant. So this particular term is a constant value. So since m dot and T0 will be constant in an isentropic flow, these two are separate, individually constant, and in order to, if these two are constant and A star P0, the product of A star into P0 should also be a constant, right? So A star P0 should be constant, means A3 star into P0 3 star P03 should be equal to A1 star into P01. It means A3 star by A1 star should be equal to P01 by P03, right? So this value is 1.397. We have obtained this value, right? So P01 first region. So P01 is based on first region. So first region means the P0, since the process is isentropic, means the stagnation pressure will be constant anywhere in that, in constant for P01 will be equal to P01. So P0, this will be equal to P01 is, since the process is isentropic, and P03 will be equal to P02 because the process is isentropic here. For isentropic process, the stagnation pressure remains constant anywhere in the section. So those important concepts you should be thorough. Then only you can apply these equations, right? So if and only if you are thorough with the basic concepts, what are the basic concepts for isentropic flow? What are the basic concepts for in the case of normal shock? Should be thorough. Okay, then only you can apply those things to solve this problem. So you can write it as P0. So this will be equal to P0 1 by P02. 1 is the upstream of normal shock. 2 is the downstream of normal shock. So students, P01 by P02 is obtained as 1.397, means P02 by P01 is inverse. You will get 0.7157, right? So students, if you got the P02 by P01 ratio across a normal shock, you can obtain the upstream Mach number, right? How? Because there is a table for normal shock table. There will be a Mach number, m will be there, so many values corresponding to Mach number 1. P02 by P01 will be there, so many value. So in somewhere in between, a particular value of P02 by P01 will be around 0.7157, right? So corresponding to 0.7157, you will obtain a Mach number 1. So that particular Mach number 1 will be, you can obtain from the table as M1 as 2.02. Should I show you that table? Okay, I will show you. Students, have a look at this normal shock table. You can see that corresponding to P02 by P01, that is P0y by P0x, the value where its value becomes 0.7157, means around 0.712. Corresponding Mach number x will be 2.02, right? Okay, so you have obtained corresponding to So 0.71 to 2.02. So you have obtained M1 is obtained. M1 equal to 2.02. So corresponding to 2.02, what is M2? M2 is obtained as 0.574. So M2 is not required here actually. Now what actually we are asked to find? We are asked to find the location of the shock, right? Location of the shock. So corresponding to M1 as 2.02, you can find A1 by A star. A1 by A star value from isentropic table of isentropic. Students, since the process is okay, the process here is isentropic here in this in the region 1, the process the flow is isentropic. You can have the if the value of m1 is known here, so this particular m1 is known, you can calculate a1 by a star if this particular Mach number is known. Since the flow process is isentropic, you can use isentropic flow table for corresponding to m1 as 2.02, m1 2.02, a by a star corresponding to m1 as 2.02 is how much? 1 point sorry, around 1.71, right? So that value is 1.71. So A1 by A star, actually that A by A star means A1 by A star, because M1 is taken. So A1 by A star is 1.17, right? Also corresponding to the inlet Mach number Mi equal to 1.7. So Mi is 1.7 already given. So students, wait. So A by A star corresponding to A by A star corresponding to Mi equal to 1.7 will be obtained like how much, since 1.7. So here 1.7 is not given. So in the previous page you can see that. So here the 1.7, okay, you can see here 1.7 corresponding to 1.7 is A1 by A by A star. So AI by A star corresponding to Mi equal to 1.7. So here I means here also I. So A by A star corresponding to M equal to 1.7 is A by A star. So its value is around how much? 1.337, right? So that we have already obtained. So 1.337. So we have the value of A1 by A star is known as 1.71. AI by A star is known 1.337. So you can obtain a relationship between A1 and AI. So A1 by AI, so you can divide, so if you divide the value A1 by AI will be 1.71 by 1.337. Okay, so you will obtain, gives A1 will be equal to some 1.27 AI. So if the value of AI is known, A1 can be obtained. So the shock is located at a section where the area the area of the section is 1.27 times the inlet area, though the location of the shock is where the area of the duct becomes 1.27 times of the inlet area. So that is how location is found out. So this is enough. Since the area of inlet is not directly given, you don't need to find the area of shock. area at where shock is. You just need to arrive at this location, arrive at this particular expression. Now the second question was percentage loss in stagnation pressure. Percentage loss in stagnation pressure. So that is P0 across the normal shock. P01 minus P02 by P01 into 100. So that is what we have to find. So it will be 1 minus P02 by P01 into 100. So actually P02 by P01 is already obtained, 1 minus 0.7157, right, into 100. So it will be around 28.5%. 28.5%. Now change in entropy. S2 minus S1 is also asked to find. So it is nothing but R log P01 by P02. So 287 log P01 by P02 is 1 by 0.757, right? P02 by P01 is 0.757. So it will be around 95.95 joule per kilogram Kelvin. So this is how you find change in entropy. Okay, so the question is solved. So hope you have understood how to find the location and all. So very important point is that you should apply a particular equation here. What was that equation? Okay, this equation. Should not to apply this equation because upstream and downstream of the flow is isentropic. So for isentropic, A star P0 will be constant. So that particular point very important. So you might not be able to apply this equation if you don't remember, if you don't know the concept. So there should be this concept you should remember always in case of isentropic flow. Even if whenever you are in short of some data, you don't know to proceed in the problem, what to do. You won't be knowing what to do because there is a shortage of data. Means you might be missing this particular equation. So if you know this equation, you will be able to relate A star and the critical area and stagnation pressure, right? So with this, I will stop this session. Try to do as much problem as you can, and I will give you some assignments. Thank you.